Okay, so hello and welcome to the second part of the chemical equilibrium notes. This part is specifically for students who think that they might take AP Chemistry or AP Biology, and so this will give you the background that you really need so you're not having to learn a lot of crazy new things right at the beginning of those classes. So we can write any sort of reaction like this, with the little numbers being the coefficients and the big numbers being whatever the chemical species are. And so when we do that, we can end up writing K, okay? Remember, K is the ratio between the products and the reactants. And so we're just going to do this in a little bit more detail. And we write it with putting the products on top, the reactants on bottom, and there's a very specific way we do that. We use the concentration, that's those brackets, remember, and then we take the coefficient and put it up there. So if we end up with 2 of those C's, that means it's kind of like twice as important. It really increases the chances that we'll have a collision and have a reaction. And so that is why we're going to end up using that coefficient up there. So with 2, you would take the concentration of C squared. You had a 3D, it would be the concentration of D to the third. The one thing to note is that on both the top and the bottom, you only include aqueous solutions and gases. You don't include liquids, you don't include solids, because they don't have concentrations. Their concentration is moles per volume. And I mean, I guess they have a concentration, but it's extremely high, and it would mess up our reaction. And honestly, like especially in an aqueous solution, if we're thinking about some reaction happening, like carbonic acid dissolving, there's all this other water involved, and we don't care about that other water. The reaction we care about is the carbonic acid and the H's that leave from the carbonic acid and affect the pH. The rest of the water is just making it more dilute than it might otherwise be. So don't include liquids or solids. If they're there, just ignore them. Okay, and so again, if K is really big, it means you have mostly products. If K is really small, it means you have mostly reactants. And notice the scientific notation. If you're going to be taking AP Chem or AP Bio, you need to get used to scientific notation because it's going to be everywhere, especially when you're talking about equilibrium. You know, we think of something, oh, there's a lot. The ratio is 3 products per 1 reactant. Chemists don't think like that. They think, oh, there's a lot. The ratio is 1 million products to 1 reactant, or 1 million reactants for every 1 products. And so they end up using scientific notation a lot. So when you talk about acids and bases, strong acids and bases aren't really reversible. I mean, they are, but they're basically not. You can assume that all of the H pluses on like hydrochloric acid go off into solution, and they're not going to come back and become HCl again. They're just not. But weak acids and bases are reversible reactions, and they do happen with the reactants breaking into the products and the products breaking into the reactants and back and forth. So you're going to see a lot of times the notation for this as HA as a weak acid. So the A might be the bicarbonate, or it might be the acetate ion. It's going to be whatever is in the acid that's not the H plus that's breaking off. So the example here is the acetic acid is HC2H3O2. And so the A is this thing here. Everything except for the H. So when we think about it for weak acid, the equation is the whole thing breaks into the H plus, and then the rest of it with a minus sign. It's the acid, the hydrogen ion, and the conjugate base. If you're not sure about conjugate bases, go back and watch the last video, part 2, where we really talked about conjugate acids and conjugate bases. And so we can write the Ka expression, the concentration of the hydrogen ion, the conjugate base, and the acid over here. Remember, there's a water that's involved over here and makes an H3O+, but we don't worry about waters. So we can use this to describe just how weak is a weak acid, meaning how many of those molecules, what fraction of them, what ratio of them actually break apart to form the H+ ion and the conjugate base. And so here's acetic acid. Again, we ignore the H2O. And when we plug it in, what we find is that for a 1 molar solution, this matters. If you used a 0.1 molar solution, it would be different because, look here, these are concentrations. But for a 1 molar solution, which is kind of the standard solution to compare, our K is 1.75 times 10 to the negative 5th. Think about that for a second. What does that tell us about the ratio of products, and products includes like the H pluses, to reactants? What it says is that, wow, not very many of the acetic acids actually break apart. Like, only a tiny fraction of them break apart. Most of them actually just stay as acetic acid with the H still attached. But let's compare this. How is it compared to some other acids? So here we've got acetic acid, weak acid. Here we've got hydrofluoric acid, another weak acid. Well, what does that tell you? What does that tell you about the ratio of products to reactants? Okay, and remember, that includes H+. What does that tell you about which acid is weaker? As in, like, produces less H+ ions. When I look at this, I see that this ratio, still very small, but it's closer to 1, which means that more of the reactants break apart to form products. Acetic acid has a very small Ka compared to hydrofluoric acid. I mean, not that much smaller, but smaller. And so that means it breaks apart less than hydrofluoric acid does. The more things break apart, the stronger they are when we're talking about acids and bases. So hydrofluoric acid is stronger than acetic acid. So think again now. Hydrofluoric acid is stronger than acetic acid. Remember, we're talking about the same molarity solution. You have to compare the same molarity solutions. Which will have the more acidic pH? Well, which one has more H+ ions? Okay, so let's just look really quickly back at our reaction between carbonic acid, okay, CO2 dissolving in water, make carbonic acid breaking apart to release an H+ ion, that H+ ion going and making a mess of calcium carbonate. And the one thing I want you guys to understand is that these are reversible reactions, but really, they don't actually happen all that much. Okay? All of these have K much less than 1, which means that their ratio of products is much smaller compared to the reactants. The thing is, though, that like small changes can make a big difference. So these things don't happen a lot, but when they do happen, they are important. Okay, so that's it for today. Thanks.